Okay, so what you just did with your puzzle, we talked about entropy. Haven't really talked about free energy though, but that was in your homework. Free energy is the same thing as Gibbs free energy, that capital G thing. So thermodynamically favored processes, that's the same thing as a spontaneous process. When I see spontaneous or thermodynamically favored, like in my head, what I think, and maybe you should write this down, is I think happens all by itself. Happens without outside interference or assistance, happens all by itself. And so when I read a question and it says, is this thing, whatever it is, thermodynamically favored, I think, will this happen all by itself? And so proceeds without any assistance from outside of the system. Water's going to evaporate all by itself at 25 degrees. Iron rusts in the presence of oxygen and water. And sodium chloride is going to dissolve in water. And that's actually not totally true. You have to put a little bit of energy into it. Was it like 4 joules or something stupid? But we'll just move on with our lives. I don't know if you remember that, but that's the thing. So stuff that doesn't happen by itself, non-thermodynamically favored processes, they have to have assistance from the outside. So water doesn't boil at 75 degrees Celsius. Like you could leave a pot of water on the stove forever and it wouldn't boil at 75 degrees Celsius. Water does not freeze at 15 degrees. And then that doesn't happen either. This is the process of refining iron ore. That's what that is, by the way. So anyway, a process that is thermodynamically favored in one direction is going to be non-thermodynamically favored in the other. That's hard to say. Non-thermodynamically favored in the opposite direction. And the reason for that, if you've done your homework and you know about Gibbs free energy, when we have the Gibbs free energy for a reaction going this way, when we go in the opposite direction, you're going to flip the sign. And so one way you'll have a negative, and that means it's going to happen all by itself. And then the other way would be positive, and that means you'd have to put work into it. So anyway, thermodynamically favored, water freezing at negative 10 degrees Celsius, and then water melting at 10 degrees Celsius. That is not thermodynamically favored. So pretty straightforward. This is my favorite chapter. It's like, oh, I get it. And I don't know if y'all feel me. I'm being very cautious though, because a lot of times when I get stuff, that's not good for you. And so I learned my lesson, so I'm trying to be really straightforward. Exothermic processes are often thermodynamically favored. That's not always true. That's not always true, but they usually are. And so the reason for that, do you remember, we've done this so many times, there's a graph, right? And then the ball rolls to here. And so that's at the lowest place for energy. Exothermic reactions, we can actually draw a reaction thing. So an exothermic reaction is going to probably have, activation energy that's involved in anything, and then the energy goes down, right? And so exothermic reactions, the energy, when you're finished with the reaction, is lower, and so things in the universe tend to go towards lower energy states. And so that's why in exothermic reactions are usually thermodynamically favored. That's hard to say. I can't say it all pretty. So in an exothermic reaction, the bonds in the products contain less energy than the bonds in the reactants. And you'll see that a lot in questions. They'll word it like that, and you have to kind of, if you can't think your way through it, give yourself some numbers, right? And so the bonds in the products, right, are less energy than the bonds in the reactants. So just give yourself some numbers, right? And it's oh, okay, and that could be joules or whatever. And so obviously energy was lost. And so a lot of this stuff is really abstract, but if you take a second to try to draw it out on paper, it really does help. Whether it's an ice table or a conversion or a picture of atoms. So there you go. Endothermic reactions can be thermodynamically favored. They can be under the conditions that entropy still increases. So that's evaporation, right? When water evaporates, that takes in energy. And I just remember teaching regular chemistry. People get confused about boiling and freezing. And boiling, you have to put energy into it. You have to take that pot of water and you put it on the stove, okay? Boiling is endothermic. And for whatever reason, people just think exothermic. And I'm don't understand why. Because I guess it's hot when you cook it. I don't know. But you have to like think your way through it, right? And then freezing is exothermic, and that just blows everybody's minds. But that's why you have to plug the freezer up, because at least you see these things are cool. See, for me, that's crazy. But you have to think your way through it, right? Of course, freezing doesn't, it doesn't take in heat. That doesn't make sense. So I would warm it up. So anyway, the reason evaporation is thermodynamically favored is because entropy increases. Because you take a liquid, which is kind of like all chilling in the bottom of the container, kind of close together, and then it turns into a gas, and so this is all over the place, and it fills up its container, does whatever it wants. Okay, so dissolving soluble compounds is thermodynamically favored, and like I said, entropy also increases. So you can have an endothermic reaction happen all by itself if entropy increases. So, and that's usually going to be at a particular temperature. So, like I'm not going to get salt to dissolve in super cold water. That's not going to work. Okay, and water isn't going to evaporate in cool temperatures. We're getting there, okay? So entropy, what does that even mean? It's the measure of a disorder, the disorder in a system. The greater the degree of disorder is favorable. So entropy in the universe increases, second law of thermodynamics. So if things are getting crazier, then it's going to happen all by itself. And this is the same little formula. It's on your formula sheet. I actually haven't seen any questions like this on an AP exam where you just take them and subtract. I haven't seen any of them, ever. Maybe have seen one with like bond energies or something, and then with bond energies, you don't use that formula. So, I don't know. If it's on there, it's on your formula sheet and you subtract, it's very straightforward. But anyway, increases in entropy are favored. Your house gets dirty, makes... I would disagree with that. This takes too much energy, so no. No, that doesn't happen all by itself. This happens by itself. This does not happen by itself. This is what you pay people to do.
Stir-fried natural habits.
Yes, spilling a glass of milk. This is my life. These things happen. This is what happens. Nope. You just come live with me for a day. You'll see some entropy. My son took a roll of tape, a beautiful roll of tape, and he taped his whole, it's rolled up and beautiful, and it was the kind, it's like the pop-up kind, so it came off by itself, and I was like, you can play with the tape, because I was trying to do stuff. I was like, this is fine. How much tape can he get into? Kid had tape all of his leg, and I was like, he's like, tape makes you all better, Mommy. I was like, that's Band-Aids. Whatever. He was quiet for a while. It was fine. It was bad. Anyway.
Oh.
What?
My little brother, we had 2 rolls of Scotch tape, and he used all of it to tape my door shut so I couldn't get out.
Small children are a prime example of the second law of thermodynamics, because you feed them good concentrated energy and they turn it into a mess. I'm gonna quote myself on that and put it on a t-shirt. So first law of thermodynamics, energy is constant. It can be changed from one form to the other, but it doesn't increase or decrease. And then entropy in the universe is constantly increasing. Yay. So what kinds of questions you are going to see on the AP exam, they're going to give you a situation where you melt some ice or whatever, or they'll give you 4 of these and they'll be like, which of these involves an increase in entropy? And so to me these are really straightforward if you think about them on a particle level. So you have to think about them on a particle level. Like in your mind you have to think about a solid chunk of ice where the atoms, or molecules are in a fixed position and then they move into a motion kind of flowing mess. Okay, so that makes sense. Vaporization, same thing. Reactions were products that are in the same phase as the reactions but contain more particles. And so if you have a reaction where you have 1 mole of gas and it goes to where you have 2 moles of gas, or 1 mole of this gas and 1 mole of this other gas, you just count up the particles on each side. If they're in the same state of matter, then entropy increases. Be careful here, because if these are all gases, that works, but if this is gas and then you have 2 particles of both that are solid, entropy has decreased. So be careful if they're in the same phase. Does that? There. Making most solutions some solutions that doesn't work for. Adding heat, increasing the volume. When you increase the volume of a gas, you have increased the area that it can be in and travel around, so you have kind of given it increased probability of where it could be, so you have increased the disorder, okay? So, kind of like having a kid in a giant auditorium versus a small room, just the same. This is a good analogy. Thank you so much. I will win. I'll give you $3. Thanks. $5,000 waiting to happen right here. Probably not gonna happen.
Did you just
What?
Huh?
Did you just say?
Yeah, because he wrote me a letter of recommendation.
Wait, who was
Who
that?
was it?
Yeah, who was that?
Dr. Butler?
Oh, I didn't see this.
Okay.
Did you see it?
I did all this. This happened. Okay. Okay, so like I said, you have to think about it at a particle level. When you have solid water, they're very organized and close together. But when it's a liquid, they can move around and flow, and they're not as close together. So entropy has increased. It is more. So if you take and you freeze water, wait, just kidding. If you just act like I didn't say it. If you take and you vaporize water, this actually has even a larger increase in entropy. So, yay. We're kind of revisit. A lot of people will do what I'm doing right now. Remember when we had done like calorimetry and all that stuff? A lot of people will do it then, like chapter 5 stuff. But I don't know if that would have worked. I kind of like it now. I need a break. Anyway, so entropy is also increasing when products have more particles. And so here you have this big organic molecule, and it breaks up into 4 different things. So you have 29 gaseous molecules. Even if it had taken 4 liquid molecules and broken them into 4 gas molecules, that would still be an increase in entropy. This is like to the extreme because you have more molecules. Increasing the number of moles increases the number of potential arrangements, and anytime you have a larger kind of not probability, you have a larger variety of situations and combinations to choose from, then that kind of increases your entropy. Changing liquid to gas also is going to increase the number of potential arrangements because they can move around the container instead of being at the bottom of the container. This stuff is, yeah, okay, this is pretty straightforward, right? You good? Yay. So entropy is usually positive when you make solutions with solids and liquids, because an ionic compound, we talked about the lattice, how they're nice and organized and in a little matrix, or called a lattice. But when you make a solution, they spread out. Ow, float around. That's on tape, nice. And so entropy is going to increase when you also dissolve a gas in the liquid. So the rapid and chaotic movements of the gas are going to increase the entropy. So.
But what about like whenever I'm just regular, like what if water breaks into oxygen?
So that's electrolysis, and that's actually in the next unit. But that's going to make, when you do that, it breaks into hydrogen and oxygen gas. So increase in entropy for sure.
Oh, it is.
Yeah, and it's actually, that process is not going to happen on its own. It's not thermodynamically favored because it's endothermic to the extreme. So you have to put electricity to it, and that's how that happens. It's good. I have a little kit where you can do electrolysis. I want to do it, but I don't think we'll have time. So when you are going to be looking at adding heat as you go through, entropy obviously increases. I think I've said this a couple times already. Moving on. Look at these guys. Do you remember this? Do you remember what this is called? Maxwell-Boltzmann distributions. You'll see this on your final. You'll see it on your final. You look bored. That's good because you remember stuff. That was a long time ago. So remember this. This is what's going to happen, y'all. I'm trying to help you. I'm trying to help you be successful.
Is Coulomb's law going to come back?
What?
Is Coulomb's law going to be in this chapter too?
A Coulomb is a thing for next unit. It's a conversion factor. Coulomb was all up in the electronic stuff. There. What's going to happen when you see these things? They won't tell you the temperatures, and you have to. This looks hotter, but it's not. Because you have to look at energy, and so you have particles spread over a larger energy spectrum, and so entropy is going to increase as you add heat. Thank you, Maxwell and Boltzmann. We appreciate that. This was never part of the like original chemistry curriculum, by the way. Like this is not, it's not a thing. So entropy is going to increase when volume increases, and then the opposite is true. And I've seen a lot of questions where the opposite is true. Like they'll take a gas, it'll be at 1 atm, and then they'll put it at it'll be like 3 liters. And then they'll put it in a container with 1 liter, and so you're decreasing the area that can travel around. Like I told you, you put it little kids in an auditorium versus the little room. The auditorium is going to be a lot crazier, right? And so, higher entropy here in a larger area or volume in this case. So be careful with that. So same thing here. You're going to be doing the stuff from the table in the back of the book and subtracting them. The thing about entropy, and this will screw you up every time, it's going to be in invisible numbers, and then you can't see it. That's funny. It's going to be in joules per degree Kelvin, and so the thing is, it's not kilojoules like the other ones. Were you just joking on that one?
Yes, I just
Okay.
did.
And so when you go to do these, thank you so much.
Go for the
Yeah, just Google it.
Right in front of her. Go put it in his
Just
chair.
do-
Go into his
just
office.
do-
Go get a
Go
bag.
in his office, just like put it in the
recycling bin.
Yeah, they can come back in the room and do it, right? Anyway, when you're doing this with the other ones, they're going to be in kilojoules, so be careful. The little s is just regular J. So that'll mess you up. I remember this summer when I was learning all this, she didn't like come out and say that, and I had to figure it out myself, and I was like, I've made a massive discovery, and it was screwing everybody up in the class, and so the nice 19-year-olds behind me, I helped them out a lot. They're like, you're so smart, and I was like, okay, I'm done with puberty, maybe that's what it is.
Say what you say again.
That's on the recording. That's on the recording.
No. I was so intimidated by this class, but then I realized that like the people around me were not grown up yet, and so I was like, I got this. It's fine. So anyway, the entropy for the reaction, to calculate this, you would take the products minus reactants. I feel like you guys have already done this in your homework, and it was pretty straightforward. You're gonna have some practice, but I would kind of. There is. How to do that, you look at the coefficients, you're going to get some practice on this. And you subtract them. This is in a table in the back of the book. I haven't seen any of these. I don't think there's any on your tests. I don't think there's any on the AP exam, but that's the thing. So anyway, how can you tell if a process is thermodynamically favored? This was on your quiz a couple times, yes? So exothermic reactions are going to be favorable. And if you make a bigger mess, then it's favorable. So if you have these two things, if it's exothermic and entropy increases, then it's always favorable, always. This is that little box. Do you remember the box?
I didn't understand.
Yeah, I didn't either.
It was so confused.
I got the.
So I
I
just
got
always
you.
look at the formula and just see whichever one makes it big.
I
Yeah.
got it, right? Okay.
I believe
So this, are we good here? Like this always is favorable, this is gonna happen all by itself. I mean, if you got this, then you're okay. So we're getting to the other boxes. If you want to determine if something is thermodynamically favored, you have to check to look at has the entropy of the universe increased, which means either the system or the surroundings or whatever has more entropy, or both, and then the Gibbs free energy formula. And so this is what you're talking about, right? The cute little formula. And so Gibbs free energy is helpful. If it comes out negative, then you know it's thermodynamically favored. So the surroundings and the system make up the universe. So entropy has to increase in one of those or both of those. So if the entropy of the universe is greater than 0, the reaction is favored. And so, yeah, I know, like this is a nice formula, but this isn't a thing. Okay, so heat flows link systems to the surroundings. Exothermic reactions, they're going to increase the entropy in the universe because heat is going to, into the surroundings because they're going to speed up the molecules. We talked about that a second ago. Were y'all okay on that? So if the system loses heat, then the entropy of the surroundings is going to increase because you're heating them up. They're going to move around faster and have more arrangements. Are you okay on that first part? Alright, so the entropy of the surroundings is going to decrease in endothermic reactions because energy is going to be pulled into the system, and so the surrounding, whatever they are, water, air, whatever, they're going to be slowing down. And so you're going to have less energy and less arrangements. You okay on this? Who said no? He says yes? You guess. I think if you think about it, any reaction, you're going to have a change in energy, right? And so you have to just think about which one is receiving the heat, and then wherever the heat's going, that's going to be making a mess and making it more chaotic, and the entropy is going to increase. And that kind of goes back to AP Environmental. I'm sorry if you hadn't taken that class, but most of you have. When we talked about when we drive cars or we do respiration, most of that energy that's lost is heat, and so that's an increase in entropy, and that's what allows that to happen. But I think drawing this on your paper, if you're having trouble visualizing it, would be helpful. So if a process increases the entropy and is exothermic, it's always going to be spontaneous, and that's what I just had on the slide like 3 ago. It also must be thermodynamically favored, and that's going to be thermodynamically favored. I'm done with this little formula. All right, so yay. So this is the part that has the little chart that's confusing apparently. So Gibbs free energy, like I said, this is in kilojoules. All right, the temperature, Kelvin has come back to visit. Hello, Kelvin. Nice to see you. So, and then the enthalpy, again, is kilojoules, and then entropy, that's wrong. That's totally wrong. Y'all know I'm right. That's wrong. I'm changing it. All better. It's fine. I know. I'm sure. Okay. Anyway, so if it's less than 0, it's thermodynamically favored. Is there everything on this screen that you get? Anything that you don't get? Are we good here? So let's think about it. Go through like the easy one, right? If it's exothermic, then the enthalpy will be right negative. So if this is an exothermic, then this is a negative number, and this will be a positive number. And so you have a negative number, and you're subtracting a positive number, so it's going to be even smaller number when you're done. And so this has to be negative to be favorable. That's like the give me one, right? Now, if I go the opposite of that, if I have an endothermic reaction, and this is what happened? I have an email. Oh boy. Oh, I can't wait. If I have endothermic reaction, then the enthalpy is going to be positive. Now I'm trying to get a negative number out over here, right? That's going to be positive, and if entropy actually decreases, if it becomes more ordered, this is going to be a negative number. So I have a positive minus a negative, so a positive plus a number. There's no way that's going to be negative. So those are the two extremes of it. Okay? If you can do, I'm trying to build on this, like, that's obvious, this one's kind of obvious, and then we're going to get to the other two. And I have to explain that with water. It's fine. So you're good here? Absolutely. And so that is not spontaneous, not thermodynamically favored. Do you have a question, Matthew?
No, I just said,
Woo! You're excited you get something?
you said, are you good?
Woo! I'm good too. Woo! Oh, no. Dang it. Woo! I'll do a couple more slides. We're not done yet.
Teachers and students, please pardon this interruption. One quick announcement. This is for the Bartow County College
Fine,
and Academy
done.
students.
We'll finish this tomorrow. We only have a couple more slides and you can do some
American
practice.
Lit. You will be taking your state assessment here on Woodland High School campus.